Does that look like a circle? Is it circular? The Microsoft Teams stretches or squishes my windows. That's what it would look like without me compensating for that. So, okay, so this was going to be a little bit of a different presentation. One thing, it's going to be completely live, and I love being interrupted. So if you have a question or possibly an objection to anything I say, please shout out and I will try and address your question. So this presentation is called KnotPlot Redux, and KnotPlot is something that I started as a course project over 30 years ago, something that I hid from my supervisor and that sort of thing. And this is not as much of a Redux as I was hoping to. In fact, well, it is a KnotPlot Redux. Basically, the Redux project is a several-year project to re-implement KnotPlot in kind of a more modern way, and also to refresh the user interface so it's more approachable and usable for people. The user interface part is not quite there yet, but there's a lot of internal things in KnotPlot that I am going to show you. So I want to just first give you an introduction to what KnotPlot can do. And it's a general purpose program for use by people who are studying knots and want to maybe create illustrations, either lightweight encapsulated PostScript illustrations for publications, or super fancy, high quality color images for posters and that kind of thing. But it also can be used for experiments. Maybe you're interested in creating certain kinds of random knots, and there's all sorts of ways to do that. There's KnotPlot comes, actually, so could someone grab me a water bottle? Because I usually don't talk too much, so if I do talk and I might start to lose my voice. So anyway, it comes with thousands of knots. There's all sorts of commands to create trillions more, and you can export the models to whatever software you might need, either surface models or paths for initial confirmations and simulations that you may have. So I'm going to assume that there's a certain amount of knowledge of knot theory because we're at this conference. Oh, I forgot to actually thank the conference organizer, Renzo, for the invitation, and also for the center for putting on such a fabulous experience for all of us. And so that's really, I'm really grateful for that. So KnotPlot plots knots. And I should say that they look like they might be smooth tubes, but underlying, they're actually all piecewise linear, so just remember that. But so the smooth tubes are for fancy display. And it's going to reset this. It comes with the entire Rolfson catalog of knots and links, and that's included in multiple different forms. And you can load any one of those. And everything that you're going to see that I'm doing graphically could also be done in a script. And in fact, in a script that can even run in non-graphics mode. So if you want to run it on a cluster computer and multiple copies of KnotPlot running in non-graphics mode, that's a possibility. So let me just start with sketching something or creating something. So I'm going to just create a knot by hand. So there's a sketching interface, and so if I go under and go under and go under again and close that up. So this started, actually, I have to credit possibly the most important person in this work is Dale Rolfson, who, when I started grad studies, thank you, he was looking for someone to implement a knot program. And so that's when I started KnotPlot. And so he kindly provided me with all the initial data. And he was looking for, and at that time there was a bunch of people. John Simon was another one. Long term, he went to grad school with Dale, and they were interested. There's in the community they were interested in putting a knot in like thick treacle or something like that, and applying forces to it, and seeing what does it do, how does it evolve. And so that's how I started this project. I'm not sure what that is, but I'll dismiss it and I'll put it away. Okay, so what I'm going to do is apply some forces to the beads. There's two forces. There's an electrical propulsive electric field type force, and then there's a attractive. There's the force vectors. There's an attractive spring force along the edges, and I'm just going to speed that up a little bit. Anyway, it's probably not hard to see that that is actually not knotted. So let me sketch something that instead is actually knotted. And the way to do that is just to, sketch, something that's an alternating knot. And so that doesn't look very pretty, but if we apply the forces to it, it relaxes into something that might look a little bit smoother. And so I guess we have a square knot there, or gurney knot. So that's the one thing. Oh, I remember to interrupt me if you want. So there's a lot of forces in KnotPlot. I'll show that a little bit later. There's about a dozen different force models that can be used for different purposes. So as you know, the problem of detecting knottedness is a difficult one, and is everything on the screen? Oh, so this is not the way it should look. This long stretchy thing. This is because of the Microsoft Teams stuff. Anyway, so there's a classic problem: is something knotted or not? And there's two things here: unknown 1 and unknown 2, and they only differ by a single crossing. One of them is the unknot, and one of them is the trefoil. Who thinks that, say, unknown 1, which is showing right now, is the unknot? And who thinks it's the trefoil? Who doesn't have an opinion? So let's just see what happens. So some people voted for this one being the unknot. Let's find out. So in fact, that is the unknot. And that beautiful deformation is, there's no intelligence there. It's just balancing of forces and a smooth rotation, nothing else. And if we just pull that crossing through and check this one, that actually is the trefoil. So that's kind of cool. And another example similar is one that was originally due to Michael Friedman. And I think I may get this wrong, but I think he proposed that the left half or right half of this thing might be an example of something that would be difficult to undo using kind of an energy minimization model for relaxation of knots. I don't actually use energy minimization. I use forces, which you could think are equivalent, but they're actually not, and I'll explain that if anybody's interested. So anyway, let's try see what happens with this thing. And so also Kushner and Sullivan in a paper did a very nice relaxation of not relaxation, untying of that. So that's also the just an unknot.
Rob?
Yep.
I have a curiosity. Suppose you go back to the example you took from Michael Friedman, and you specify your force proportionally to the curvature, local curvature. Maybe you did. I don't know. Would you get different evolution? Same result. Maybe.
You would absolutely get something different, and I don't use anything with curvature. That wouldn't be hard to implement. As I said, there's this kind of in KnotPlot, there's kind of a parameter explosion, and there's so many different ways of doing things. That's actually interesting things for maybe students to explore. And there is a plugin mechanism so that if you don't like any of my dynamics, you can implement the dynamics entirely on your own, completely so. And so this is the Perko pair, and for those who may not know, there was a knot table classic knot table that for 75 years listed these two embeddings as distinct knot types, 10161 and 162. And in 1974, Ken Perko, I think drawing on the back of a envelope or something like that showed that they are in fact equivalent. So he had his proof, and this is KnotPlot's proof, and it's just that they end up being in the same conformation, and so that's a proof that they are in fact identical. And this example is a fun one. This is people who are familiar with Dale Rolfson's Knots and Links book. We recognize that this is a figure in the book, and it based on a paper by Brune. And a Brunian link is one that is linked, but if you remove any single component, so you can just select one, let's say maybe this one. If you select any component and relax it, the rest just fall apart. And so that's that. Now, there's lots of ways to create things in KnotPlot, and I'll say more about that later. There's braids, and these can be typed in as a braid word with, parentheses and exponents and all that, so you can get very complicated braids very quickly, and you can warp them. I'll say more about warping later. Warp them into and close them up into an actual knot, and so there's a few things here that I'm not going to talk about right now, but yeah, let's just go through a few things in this of creating things. One of the forces I didn't use yet is free drag, and so that's just you can grab a piece of the thing of the knot and drag it around, and then there's various ways of creating like packing of chains. Now there's a credit up here that's being obscured slightly. So Yunan Diao, one of my collaborators, gave a very excellent presentation at UBC, where I was working in the early days of me working on KnotPlot, and he's since proven to be a very lovely collaborator to work with. And there's all sorts of ways to. So these things are chains which are warped along an arbitrary knotted path. And I'll show another example of how to create a satellite knot later on in my presentation in a moment. And some of these I'll just skip for now. But since the hop vibration was mentioned on several occasions, there's just an interactive way of kind of exploring different views of the hop vibration. Let's see. So I think that I'm going to actually go to something that's kind of more applied now. And so I want to study the ability of KnotPlot to actually simplify complicated knots. An example might be that monster that we saw before. And before it was just what you saw is just the forces acting with nothing else happening. But I found that it's very useful to have two things going on simultaneously. One, deleting any vertices or edges in spaces which where you can get away with it. Because we're not doing molecular biology yet, so we can do that. And then if something gets stuck, splitting the edges. So when I click on this button, both of those will be happening simultaneously, and that thing simplifies to an unknot very quickly. And then the other example of the trefoil, it just also simplifies nicely. So there's some pretty nasty knots here, and if you get a copy of KnotPlot, and by the way, I am offering everyone who would like to have a copy a complimentary key. So just approach me sometime before the end of the conference, and you'll have to type your email address into the blue key program, and I'll send it to you. So there's some famous unknots, the Gurits unknot here. I don't have much experience personally with that, but that simplifies very quickly. But there's a few tricky ones, and this one is due to from kind of paper by Oki. And this one actually has proven tricky for a number of different researchers, although if Lou is listening, I think your group did a lovely simplification of this. And so this one will run for hours on with these dynamics, and it just doesn't seem to go anywhere. So I had a hint there, and the hint is to turn on dragging and kind of look for, maybe there's kind of a global obstacle. So if we pull that thing over, this is a bit tricky sometimes. Pull that there.
Can I ask, when you drag, sorry, how you decide where it stops dragging, I guess, how the algorithm does?
The dragging is just in the direction of the mouse, but there's also something I call rockets, which you can use the keyboard, but to push and pull the bead in the direction of the line of sight by the vertex. But that's really hard to do when you're giving a presentation holding a microphone. So anyway, so we pulled the string around. Let's see if we delete some beads, if that helps it also. In fact, it does. So it's just an unknot again. And some of these look like they're really tough. Like this one, for example. But this is actually quite relaxing to just watch. You can go into full screen mode and just sit back and enjoy I'm planning to add a feature that visualizes Ridermeister moves, maybe with sound, of course, and because you need that. So, but I'm not gonna force you to endure the whole thing. I'll just see what happens if we can get those buttons to show up again. Okay, well, maybe I'll just rerun it. And I'll click on the delete many beads button. So that falls apart pretty quickly. And so I'm not going to go through any of the others, but if you, there's actually some really nice ones that are due to, well, actually that's not the one that is from Lou, but he told me about a lovely trick on how to make really kind of nasty unknots that are very hard to simplify. So I'll leave that up to you if you get a copy of KnotPlot and run it. Just click on the unknot question mark button. They're all unknots, and they're all created with a different tangle string, which I'll say something about that in a sec. And so I think that's enough for split delete. Now let's actually see an application of split delete to some data from Carlo Berenghi. And just have to switch over here. So I guess just over 3 years ago, Carlo sent me some of his data. And Carlo, maybe just say what these are, actually, so I don't get it wrong. And so this one has 27 different components. This one has 18 different components. So I'm just going to pick, say, component 0. So I just deleted the other ones and do some initial relaxation. This looks a bit funny, but it starts to look even more funny. And so this is a connected sum of two reasonably complicated knots, and they're connected by a twisted strand. Now, if you clicked on this D beads button enough, they would eventually get into a nice kind of shape. So in my work as well with I've worked with Mario Vasquez and Javier Arzuaga from, at the time I was working for San Francisco State University, and we were doing a lot of identifying complicated knots. And currently I'm working with Chris Soteros and her group at the University of Saskatchewan, doing similar things for links. So I think that's enough of demo A. And I'd just like to show you a few other ways to create interesting knots. This thing is got to be moved somewhere. Maybe there. So If you don't have enough knots, if you want to actually type something in, say for example, using the Conway notation. So Conway wrote a fabulous paper in 1969, 1970, and he introduced a notation for creating knots. And he said, I think that it helped him enumerate all of the knots, proper knots to 10 crossings in a single afternoon, which is pretty fabulous. And so, for example, if you wanted to create a pretzel knot, 334. That's you just type in the Conway notation, and Appendix C of Del Rolfson's book has the Conway notation for the entire catalog. So the reason I'm showing this right now is that when you type in the Conway command, there's a tangle command string, which it leads me to talk about the tangle calculator. And I should say that excuse me. One of my inspirations, of course, is a paper by Ernst and Sumner in 1990 on the calculus of tangles. And so the tangle calculator is a separate component in KnotPlot. And if we type in this string, we don't type it in, we enter those. The tangle calculator is like anybody used RPN HP calculators? I love them. I'm sure lots of people here do. No. Anyway, they're stack based, and they sort of are nice because they don't really have much of a state. The only state is the contents of the stack. There's no pending operations. So the tangle calculator is a similar thing. So this is 3R. So 3 creates a 3 tangle. R is Conway's R operator, which is a rotation, basically. So 3R and then 3R. And then sharp is the tangle calculator for direct sum. So it just adds those two. And 4R, sharp. And then sharp again. Okay, well, I think I messed up, so it's a little hard for me to read the screen, all that. So let me just create a like a granny knot or something like that. 3 at duplicate. So there's operation. There's I did the wrong thing. Anyway, yeah, this is a bit hard for me to do in presentation mode. So I'll just there is a manual for the tangle calculator, and it's a very powerful thing. And so let's just move on to something else. So 32 minutes left. So one topic of interest is, say, if you wanted to know what is the minimal number of sticks or steps that are needed to create any particular kind of knot. So I'm just going to reset here and bring that down a bit. Let's just pick a knot at random. So this one's 7-7, and this is kind of in the smooth tubes mode, or so it's basically a large number of edges in the polygon. But if we wanted to actually see what the minimal stick version of that is, we just, when we loaded, we prepend an MS 7-7, and this is the minimum, possibly the minimum number of sticks that you need to create that knot type. This is some work that Dick Randall at the University of Iowa and his student Monica Meissen initially did, and I did a lot of that for my dissertation work, doing the entire proper knot catalog. There's also a similar version work done with Eric Rodden. We had a paper back at some point, and this is the equilateral stick version. And then some work that was done together with Koya Shimakawa here at this meeting was to find the minimal step on a cubic lattice version, and so this was work that was pioneered originally in 1994 by Yunnan Diao, and he found that there were, he found a collection. He proved that the only knot type that you can create with 24 steps on a simple cubic lattice was the trefoil, and that the trefoil had a certain enumeration of several thousand different paths. Well, when we redid this work in 2009, Yunnan was also part of the team, and I wanted to actually not look at the number of paths because I thought it was more interesting to look at the number of entities, like how many different trefoils could I hand you, and so this is 75. Do you see the 75? Okay, you're not hidden. No, it is hidden. So I'm just going to make this a bit smaller here. Right. So there's 75 unique versions of the minimal step trefoil. So each of these has 24 edges. Oh my goodness. And there's something really interesting going on. Of course, the unknot has just one, and these are kind of randomly positioned in space. The figure 8 knot has 76 different versions. The 8-7 knot has only one, which is a bit odd. And some of the knot types, for this study, we did all the proper knots to 10 crossings, and some of them have only one type, some have 2 or 3, some have several hundred, and some have like many thousands of different minimal step versions. And I'd like to actually put it out to anybody. Is there any meaning to this? For example, I'll show you one of the knot types is a bit suspicious, and that's this one. There's just one minimal step 10, 123. And if I relax this, oh, actually, no, it's not that. So this is a knot that has a high degree of symmetry. And so it might be related to that in some way. But if anybody wants to actually, well, first of all, the paper is available. Here's the complete list of authors. So you can download the paper, and the data is not yet available, but it will be soon. So if anybody wants to have the data before I have it officially released on this page, just send me an email and request it. And so anyway, that's kind of cool. And so I just wanted to give you an idea of how you would actually find these. To do this, we use something called the BFACF algorithm. And these are the authors at the top of the window there. And this is a way of modifying knots on the simple cubic lattice without changing the knot type. And there's various interesting properties about ergodicity and stuff, which I don't have the time to explain right now. So right now we're seeing there's basically 3 moves. There's a +2 move, which kind of pops out an extra 2 edges. There's the inverse of that, and there's a 0 move, which is just like corner like that, changing into a corner like this. So right now it's going at 1 step per redisplay, and if you just move that up to 1 million steps per redisplay, then things are much more interesting. So to get a, let's just reset that. To get a minimal step trefoil, let's just load many step trefoil, which is off lattice, and just have to put this down for a sec. It'll be okay. So I've embedded on the lattice, and I'm loading it into what's called the BFACF engine in KnotPlot. And then I'm going to click on this, and just it's just going through stuff, and now it's recording data that it finds, and It says down here that it found a minimum step candidate of 24. So basically that's how you do it. Now, again, since I love hop flinks, let's try a hop flink example. So unknot 6 and hop. And this I have to put the scale it a bit. 2, 1, 1. So I just scaled it and refined it. I'm going to embed it on the lattice, load into the engine, and just let this run for a little while. So it'll take just a few seconds, and then I'll start. So now I'm going to start recording. Not gonna. Normally, if you wanted to actually get a good candidate for a minimal step number of a typical knot, then you'd maybe let it run faster or longer, and you wouldn't look at it. So looking at it slows the whole thing down, of course. So that's a potential minimal step candidate for that 6-component hop flink. Any questions so far?
Yes, so you showed earlier some data from simulations. Is that a part of the code where you can take data and insert it, say like a list of positions?
Oh yeah, well you could just save it. There's a save command, and so you can just save the data as just a simple vertex list, and there's a various other KnotPlot exports surface models and the actual knot path in maybe 20 different file formats. So depending on what you actually need to do. And then there's also the plugin mechanism, so that can give you access to all sorts of other things.
You import data as well.
Yes, there's a corresponding load command, load and save. And yeah, so plus there is a scripting language for KnotPlot, and I'll say more about that in a little while. So time's still good. So actually, there was one fellow, I actually apologize, I forget your name, but we were just talking a little bit about random knots. And there's many ways to create random knots in KnotPlot, and I'm just going to show you. These are so there's this demo A and demo B control panels, and they are intended to be demos, so they're not fully. They don't necessarily. You have to go and take the commands that generate the demos and do something yourself. But one of these is just creating a initial random sort of mess, and allow. Now this is an optional feature in KnotPlot. You can turn off strand passage. So right now this is creating a random mess and then just relaxing it until it's in what I call a safe position. And then at this point you can prohibit strand passage again, and then attempt to simplify that. So that's just one example of how to create various random knots, and so these could be exported, and you could have your own method to do that. And this is using. So let's just look for a long time, KnotPlot had its own custom scripting language. And it's probably hard to read, but let's make it a little bit bigger. And the disadvantage of that scripting language was that it didn't really have a proper looping and if then else structure, and doing things was probably overly complicated. So I don't know why it took me so long to do this, but I finally embedded a proper scripting language into KnotPlot. This is in May of this year. And the scripting language I chose is Lua, which is a very simple and lovely language that was designed to be embedded in other software as a scripting language. And I also plan to add Python to that list. But right now it's just Lua. And so this opens up a huge number of new possibilities for doing experiments and all sorts of other complicated things with KnotPlot. So I'm pretty excited about that. And you can do some weird things like weird constructions like this, and anyway, this could not have been done easily in KnotPlot's former scripting language. So that's random knots, tangles, Celtic. So, oh, I actually forgot to say something important about the tangle calculator. So let me just reset this. So 20 minutes. So who's familiar with Conway's original paper, which is quite a fabulous thing, but he had, I just want to go back to tangles for a second, because some important thing I forgot about. So this is a very simple demo of the tangle calculator. Well, not the tangle calculator, but what Conway called basic polyhedra. I call them, and other people call them, tangle templates. And a tangle template is a bunch of strings that can be arbitrarily knotted. They don't have to be planar. And there's a number of tangle holders, which are the circular things with that L shape. That's a pictorial device that Conway used in this paper. And some things are not showing up for some reason. So, but that doesn't matter. These things are supposed to be buttons, and I don't seem to. Okay, a few things are acting weird here. But okay, well, that just embedded a certain kind of tangle into the tangle calculator, into that tangle template. But let me show you a better example. And say you started with a knot, say, no, that's not a good one. This one might be okay. So there's a bunch of stuff that goes on behind the scenes here. I'm just going to say templates. I'm not going to explain all of the steps, but okay, it kind of created not a very nice, you have to kind of start with a nice embedding. So what that did is it took every one of the crossing points and it cut a circular hole and then created a tangle holder at that crossing. So actually meant to have a Lua, very simple Lua example. I guess, I don't know what you're supposed to do. Okay. So it'll be very easy, for example, to write a Lua script that plugs in all possible plus or minus one tangles into this tangle template, and then see what kind of knot types result. So, and by the way, that's one thing I forgot to mention. There is some important software that was partly developed at San Francisco State and partly since then. And it's how do you actually determine what? So let's actually say, yeah, maybe I'll say that a bit more about that later. There's a wonderful Humpfly public domain software originally developed by Bob Jenkins from UC Berkeley, and that was modified by some other people and myself, and we are releasing that into the public domain again. And that's a very high performance computation device for the Humpfly polynomial. And so maybe that's what I want to say about that. The tangle holders. I don't think I have time to really talk about the Topo-ICE, the Topological Interactive Construction Engine, which really is the brains of that. All the smart stuff comes from Isabel Darcy, who was a student of DeWitt's, and she created a very, so if you do get a copy of KnotPlot, please click. So right now KnotPlot is kind of a non-standard user interface, but the advantage is that it looks the same on Linux and Windows. So so if you want to access the menus, don't use these guys here. That's what will change in the ultimate Redux. Just right click here and go to manuals, and Topo-ICE has its own manuals. So read that for a good introduction to. So with Topo-ICE, you can, for example, I can just show you one thing. And and I'm not going to explain this, but it's really interesting if you're interested in what kinds of, just thinking about rational knots, what is the minimal path between any two rational knots with just one single strand passage. So this is not displaying properly under the system, but this is a graph of so look, if anybody wants to see that in the way it should look, please ask me. So this is showing you that the upper left is equal to the upper right. This one's equal to that one, and you can see that they differ by a single crossing, which is in the circle. So TopOICE is a wonderful tool for exploring those kinds of things, and also there's a TopOICE R for recombination, but I don't have time to talk about that now. So, random knots field. Let's just get out of this. Reset. Okay, so 14 minutes left. So one of my interests is in, and also this is some work that Mario Vasquez then at San Francisco State University, now at UC Davis. We've been talking about this since 2010, and it's knots in the field. Now you're walking along Ocean Beach in San Francisco and you see a bunch of kelp and it's knotted, and you really want to know what knot types they are. And so this is that ultimately the tool is to figure out what are the knots, or maybe it's just a knot laying on the street or something like that, and you need to find out. So I'm not going to do that yet, but I do want to show you one little thing. And so here, so this is a very simple little program that I wrote with OpenCV. OpenCV is a public domain, very high quality computer vision package. And so what this does is you can take some images of knots. I'm just going to make these a bit bigger. And so drag and drop. And this actually has music. I like to make a lot of my demos have music. Oh, feedback. Okay, in order it does so you know, everything should have music even if it's not supposed to. So okay, well, okay, that's going to cause feedback, so we can't enjoy the music. That's too bad. So go away. So this kind of visualizes the algorithm. So just ignore these things. The first step is to oops, this needs to be put up there. So the first step is to create what OpenCV calls contours. And then the next step is to create like a thing that has kind of the crossings properly done, but they're not yet connected. So then we connect those. And this is where you get a nice musical note if it's working properly. So these ones are from the Knot Atlas. And I'll just do one more from the Knot Atlas of an actual link. Say this one. It's just so that's a way of getting a diagram of a knot into KnotPlot very quickly. And so it's it's now a three-dimensional entity, and you can work with it. So I figured, well, one thing I'm not very good at is actually drawing knots. But I did draw this knot earlier today on one of the official papers, and this is the Rob one here, and so it's actually they're not linked. So that's something that I find challenging to draw. So I asked someone who I know is a great drawer of knots and links, Koya, and he drew me this one. And it only required a minor amount of alteration. Basically, you have to kind of draw a pretty good-looking diagram currently, and I'll be improving this over time. So here's what Koya's sketch does. Anyway, so it's a very nice looking. So there's a little bit of relaxation there just to make it look prettier, and it's a very nice 10-124 as we can see. Okay, so that's knots in the field. So I'm running out of time rapidly, so I wanted to end on something which was in the spirit of the place we're in. And I can't think if you're in Italy and you're talking about knots, who do you think of? Who? Oh no, heavens no. No. You're right, that's very important, very important. But the single most important person,
Leonardo.
yes. Okay, so let's look at Leonardo's knots. So this is work in collaboration with Caroline Carciardi. She lives in California, and we met in 2010, I think, and she sought me out because I was interested in knots, and I was actually attempting to sketch or to actually trace out some of Leonardo's knots. In fact, this one, and you may have seen this. This is a etching that Leonardo da Vinci did, one of 6 different etchings. And it's really interesting to see that there's a lot of misinformation about this. And I remember there's an essay by Ananda Kumar Swamy. I only read it in a Parabola magazine article years ago. And he says, and other people have said this, that, well, actually, how many strands is there here? Just ignore the 4 corner knots, which are just, it's like this thing is separate. It's impossible to tell. But he and others claim that this has only 1 strand. And so well, some of us had to actually find it out. Let's just get rid of that for now. And this is one of 6 that Leonardo did. Also, Albrecht Dürer, I know the 2 were contemporaries. Leonardo was about 19 years older than Dürer. Dürer did a similar set, very similar. And I'm not exactly sure of the history behind that, but I think he just made copies. But so I think the originals are due to Leonardo. Or there's some feeling that there was actually a knot cult at the time in Italy. So I don't know, but I think the thing that's interesting, and then this one, just memorize it. And the interesting thing is that what was the interesting thing? Oh, can't remember what I was about to say. But now one of this paper is relatively unknown. It's by Jessica Hoy and Ken Millett, and Ken is well known in our community. And they wrote a paper on that number 6 that I just showed. And it's in this article here. I was only sent a personal copy of this, so I don't actually know where I would find it. But if anybody wants a copy, I'll just send it to you. So they talk about the symmetries involved, and that's really quite fascinating. So let me just show you a separate. So remember this one. There is a separate rendering that I did. Now with Caroline, I actually tediously traced out this entire. Oh, okay, well, you're missing a little bit of it. So this is number 3, and it's rendered according to the symmetric energy illumination energy model due to Greg Buck and his colleague, who I can't remember the name of right now. But so Greg is a long-term colleague of mine. And then there's also SE6, also a beautiful thing. And so to answer the question of how many knots does this have? I cannot do that easily at the moment, but if I have enough time at the end, I will actually show that to you. Oh yeah, there's one other thing I wanted to say. There's something that's actually I'm thinking of possibly going to if I can get there, and that's to the Sala delle Asse. And this is in the Castello Sforzenzo in Milan, and it's you know, I sometimes have to think that Leonardo was a bit of an overachiever, but of course he had assistants, so maybe it wasn't so bad. But this is a very bad image of this. But on the ceiling of this chapel is something that looks a bit like this. Okay, now this is so this is a fake in certain ways, and I'm part of the fakery. So this is work I did with Caroline, and so there's these knotted branches, interleaved branches, and there's this golden cord that goes through all the branches. And of course, claims are made about there being only one cord, and it turns out to be obvious that there's more than one. So this is a reconstruction of the foliage and the branches by someone named Maria, and no one ever told me what her last name was. And I did the tracing of the interlace patterns, and they're actually in 3D, so they can be animated, and I can show that to people who are interested later. And so I guess I'm nearly done. Any questions on anything that you may have seen? No.
Can you put a texture on the surface of the knot to make it look twisted?
Yeah, not right now, but yes. And actually, let me just, actually, I do have some time, so let me just find the actual file for number 3. And then because you're all dying to know how many components there is, right? Because it's not one, so what is it? Okay, that's something I should have prepared, of course, obviously. So I'm just going to close up, and then while questions are being asked, I'll attempt to find the actual file so I can load it for you. It's just in terms of textures, yes, here's a texture applied, which is not what you were suggesting. But so I'm just going to leave you with something else. So I think this is number 6, but I just thought it'd be interesting to take a bunch of strings and just sort of have them ram into each other and see what happens. So let's just get this going. It's only about a minute. Maybe they'll start interacting with each other. Oh. Thank you very much for your attention.
Thank you. Thank you very much, Rob. Questions?
So how many components is it? Sorry.
Okay, if you're willing to be patient, I'll just find out. 6 components. So, sorry that took so long. Anyway. Okay, buzzer has rung.